In chemistry, we deal with atoms and molecules that are just too tiny to see and too quirky and weird to represent very accurately. So we have to use models. And models don't necessarily show us exactly what the atoms and molecules look like, but they are really useful in visualizing how they behave and what they're doing when they go through a physical change or a chemical change. So that's what this video is about. Ladies and gentlemen, welcome to AP Chemistry, section 4.3, Representations of Reactions. I'm Mr. Rudolph, and in this video, we're going to look at several ways that reactions can be represented. We'll look at a list of things that a good model of a reaction should have. Then we'll look at some tips as to how to deal with those types of questions when you see them. And then we'll look at some of the questions typical of what you might see. The goal is that in a few minutes, you'll be all prepared to take your exams. So grab a pencil and let's get started. The essential knowledge statement that we need to know is pretty short and sweet for this section. It says balanced chemical equations in their various forms can be translated into symbolic particulate representations. And we're going to look at a bunch of those, starting with this one. Nice simple molecule, two hydrogens and an oxygen making water. And we know that we can represent a chemical reaction as a chemical equation balanced with the element symbols. But we can also turn those element symbols into particle models, usually little circles to represent atoms or groups of circles connected to each other representing molecules. Note that this is H2. It's a diatomic element. There are 7 diatomic elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And you should know those so that whenever you see them by themselves, they're diatomic. You'll see a bunch of those in this video today. Oxygen, same thing. And then they regroup to form the water molecules that are over there. Note that the number of hydrogens, the blue ones, is equal, and the number of oxygens is also equal on both sides. Okay, we can also represent a chemical reaction with a chemical formula, a particular model, and maybe just the names of the chemicals. Methane plus chlorine makes chloromethane, and hydrogen chloride is another way to represent that. All right, now take a look at this one. We're going to jump right into things where for example, we have hydrogens and oxygens making water again. Very similar to this one, you'll see the colors are changed a little bit. The oxygens are red and the hydrogens are white in this one. But notice they're reacting and then they're regrouping over here to make some water molecules. But if you look carefully, there's a couple of extra oxygens over here. And what are they doing? What's that all about? Well, it turns out that yes, the number of atoms on the left, the reactant side, has to equal the number of atoms on the right side, even if they don't react. Maybe you've learned about limiting reactants and excess reactants so far, and if you haven't, you can always go back and review that video as well. But how would we know that there's 2 oxygens left over? Well, here's my first tip of the day, and that is to mark up your paper. Just get in there and make it messy. All right, and here's where you can do it to keep track of all these particles is to actually start circling them. I know they make H2Os, right? So let's just circle them, that little groups that could make those H2Os, like this oxygen and those hydrogens, this one and those two, this one and those two, and so on. And after I'm done using up all my hydrogens, I still have this one and this one left over. So then it becomes clearer to me that I didn't have enough hydrogens to go around and make more groupings with those. And so as you get into particle diagram questions, don't be afraid to mark them up. I'll show you another couple of examples of that. Here we have nitrogen and hydrogen making ammonias, but again, there's 3 hydrogens left over, and that's because if I went in to mark it up, I would say this nitrogen gets those 3, this nitrogen gets those 3, and I just ran out of nitrogens. So there you go. And finally, this is one that I used in my limiting reactants video. Iodine and chlorine, note again, they're diatomic, making ICl4. And you see a whole bunch of them there. How do we know how many they're going to make and what's going to be left over? Well, start circling. And so here I was able to circle 6 different groups of ICl4s. There's the 6 molecules. And then there's one little guy left over. Didn't get a chance to react, and so he's the excess reactant. Okay, so let's take a look at what particle models must have. So you're going to be asked to choose which is the best particle model. You might have to draw one and that kind of thing. But particle models need to have the same number of each atom before and after reaction. You have to be there. Otherwise, you're going to get the question wrong or choose the wrong one at the end. Correct groupings of the reactants. So if it's an atom of an element, those are just going to be single circles. Sometimes you'll see entire polyatomic ions as a circle. You kind of have to just interpret what's there. Molecules of diatomic elements are pairs of circles, so keep track of those and make sure to put them that way. Molecules of compounds have more than one kind of circle. It should show a change in the groupings of atoms to represent new products, and any leftover or excess atoms or molecules that are shown. And again, you might have to just mark up the paper just circling the groupings. So here's some hints. First, when you see one of these, start counting. See how many of each element you have at the start and note it on your paper. Just write it in the margin somewhere where you can keep track of it. Observe how the groupings need to change during the reaction. This is unique to each question. Begin building the products, keeping track of how many you use. Don't be afraid to circle groups on the reactant side to see how many you can make. Then draw them or look for an answer with that many. Also note if there are any leftover atoms and molecules that didn't get used after the limiting reactant ran out. Put them in the final drawing as leftover, or look for them in the final drawing as leftovers in excess. Let's take a look at some sample questions to see how they might appear on one of your exams. And here we have some nitrogen and hydrogens. Again, they're both diatomic, so keep a note of that. Then they're going to do a similar reaction from the one we just saw over there. They're going to react after a catalyst is added. Which of the following is a correct particulate representation of the mixture after the reaction occurs? Okay, so if I'm seeing this, I'm going to go right up here and I'm going to start counting. I got 3 nitrogens and 3 hydrogens. Great. I'm going to start grouping them together because I know that they're going to make NH3s. All right. Then I'm going to say, all right, let's start grouping. This nitrogen is going to get those 3. This nitrogen is going to get those 3. And look, I just ran out of hydrogens. So similar to our previous example, I can make 2 NH3s, and I'm going to have 2 of those left over. So I need to find the diagram that has that. And it turns out I'm hitting it right off the bat. 2 of those with 2 left over. This one has extra hydrogens that weren't used up. This one has 3 models, which looks good, but I didn't have enough hydrogens to make those 3 models. And this one has 6 models, and I didn't have enough ingredients to make all 6. So answer number A is going to be my answer on that one. All right, let's take another one. And we're going to take some COs represented here, and then add some oxygens to it to make CO2s, which presumably are this one. So again, we're going to have to just kind of mark things up. I'm going to take a CO and make it a CO2. I'm going to take a CO and make a CO2. I'll take this one and that one. And it gets a little wonky. I'm just going to add that one over here. So it gets a little crazy sometimes. But I can see that I've made 4 groupings with one of those left over. So which of my diagrams has that? Looks like it's letter B down here. Okay, are you ready to test yourself? Here is one. Which of the following particulate diagrams best represents the reaction of carbon with oxygen to form carbon dioxide? So this isn't just pure carbon, not carbon monoxide like the last example. And we're going to produce some carbon dioxide. Take a moment, work your way through 4 of these, and see if you can pick which one is the best one. Okay, and if you picked letter C, then good job. We have 5 carbons in this one, and 1, 2, 3, 4, 5, 6, 7 oxygen O2s in there. So with 5 carbons and enough O2s to go around, I can make 5 CO2s, and we'll have 2 of those O2s left over. So that was, sometimes you have to do it more than once for a particular problem. Okay, let's take a look at this one. What if you're asked to draw a model of a reaction, which is very likely to happen especially if you're taking AP-Chem. And we're just going to start with a simple one. Here we have HF. The F is the big one. The H is the small white circle. The O is the big white circle, and another H over there. What happens in this reaction is that this hydrogen gets put over there. And so on the right, I would have to draw my fluorine, try to draw it the same size, and shade it in. And then I would have the OH and then we'd add the other H on that. So this is just a simple one with only one drawing of each thing on the right-hand side. And in this one, we actually have to draw what the box is going to look like after each one of these decomposes into a water and an oxygen. So two H2O2s make two waters and two oxygens. So I'm seeing right here that there's four H2O2s. So I can do this reaction twice. And so I'm thinking to myself, okay, I can take those four, and I'm going to make four waters, and they want me to shade in the hydrogens. And you do want to kind of spread them out and don't stack them on the bottom. If you stack them on the bottom, that indicates that you're thinking that it's a solid or a liquid. That may have changed the state, and unless that's specifically told to you, then you don't want to include that. But then I'm going to have one O2. So I have 1, 2, 3, 4 oxygens used up. I have 1, 2, 3, 4, 5, 6, 7, 8 oxygens over here. So I have to account for those remaining 4 oxygens. Okay. And those remaining 4 oxygens, because we're doing this twice, will actually make 2 O2 molecules in order to keep the law of conservation of mass going. So something like that. Now you may draw them in a different arrangement, in a different pattern, but the idea is the number of each has to count. Now we're going to look at a couple of precipitation reactions, and I'm going to challenge you with the second one to see how sharp you are right now. First, we have 20 milliliters of 1 molar sodium carbonate is placed in a beaker and titrated with a solution of 1 molar calcium nitrate, resulting in the creation of a precipitate. Which of the following diagrams correctly shows the species present in the solution in significant amounts at the equivalence point? So as we look down here, you'll notice that there's a pile of gunk at the bottom of the beaker. That's representing our precipitate. And calcium carbonate is our precipitate. You might already know that calcium carbonate is insoluble. And so I need to know which one of these best represents what's happening at the equivalence point, when the reaction is just completely done and I've added just enough calcium and carbonate to react with each other. And so I would look at all these and I'd see, all right, we have some sodium left over and some nitrate left over. Those didn't precipitate, and those appear in all of them. But over here, I have a calcium left over, a carbonate left over, and actually both of them left over and carbonate left over. At the equivalence point, that's the key right here, is that those two have completely reacted, and there shouldn't be any excess of either one of them. And so I shouldn't have excess calcium or carbonate or either. This one right here is my answer. So it's a 1-to-1 ratio for the calcium carbonate, and that's how I would navigate that one. Now this one's you're going to have to look carefully at this next one, but take a look at this picture. We have these reacting with these. These are the positive ions. The black ones are positive, white ones are negative. And we get a precipitate out here. Which of the following chemical changes is best represented by the particle diagram shown? Water molecules are omitted for clarity. Take a moment. You'll have to look at it carefully. Pause the video and see if you can come up with a guess. Pay attention to the mole ratios. Okay, when I did this, I came up with choice A, and here's why. I'm looking at the positive ions over here. They didn't make it into the solution over here. They presumably became part of the precipitate, and I also noticed that there's 8 of them. The big white ions didn't make it into the solution over here. Presumably they're part of the precipitate also, and there's 8 of them. So 8 of those must have reacted with 8 of those, which tells me it's a 1-to-1 ratio. And I'm looking for a precipitate which has a 1-to-1 ratio. Now that includes this one, and this one. Oh, that's not a precipitate. And then I got to think about what's left. Okay, what's left is that I have 4 of the positive ions and 8 of the negative ions. So the soluble compound is actually in a 1-to-2 ratio. Now this one's in a 1-to-1 ratio, and this one didn't even produce a precipitate, and so I'm looking at this one in a 1-to-2 ratio, and the precipitate in a 1-to-1 ratio. So if you got that one, you've pretty much mastered what you need to do. Let's take a look at 2 more real quick to finish off our video. Nitrogen and hydrogen react to form ammonia again. The diagram shows nitrogen represented as darks and hydrogen as lights. How many ammonia molecules would you draw if the reaction had a 50% yield. So an added little wrinkle here on this one. All right, so if you want to pause the video, you can, but I'm just going to start marking things up on here. Now I'm thinking to myself that I can get, there's 2, I can get 3, I can get 4, I could get 5. Don't worry, I'm not going to actually get 5. I can maybe get 6. Sorry, I messed up right in there, and I got those grouped correctly now. So by grouping on my diagram here, I can see that I have enough hydrogens to make 6 NH3s. I would still have a nitrogen left over, but I can make 6 NH3s. But I'm told the reaction had a 50% yield, and so the only ones that I should draw is actually about 3 of them. So 50% yield on that. All right, and here is the last one, a little challenge for you as well. The diagram represents a collection of carbon dioxide and water molecules, which are the products of the complete combustion of some hydrocarbon. And you might already know that hydrocarbons plus oxygens make carbon dioxide and water, and here's the representation of the product side. Now we got to work backwards to the reactant side. They tell us it's complete combustion, which means that all of these carbons and hydrogens must have come from the combustion of a hydrocarbon. And so, what is the most likely molecular formula for the hydrocarbon? Take a moment, pause the video, and I'll see you back here in just a second. Okay, so here's the equation that we're dealing with, and we work backwards, and you'd probably be kind of forgiven if you would have picked letter D, because there are 4 carbons and 16 hydrogens in the final result. But actually that chemical compound doesn't exist. We're supposed to know a little background information. C4, with 4 carbons, you can put up to 10 hydrogens on them because carbon can have 4 bonds max. And so C4H16 doesn't exist. C2H8 also would work mathematically here, but C2H8 also doesn't exist. So 2 carbons only has enough space for 6 hydrogens on it. But 4 and 16 is a 1-to-4 ratio, and CH4 is also in a 1-to-4 ratio. There's no reason it has to be 1 molecule of hydrocarbon over here. In fact, in this case, it's going to be 4 molecules of the hydrocarbon, and CH4 is the more plausible answer, even though these two do have the right ratio. So we kind of have to get a little deeper into that. Well, I hope you found these models helpful and that you'll be prepared for the types of questions you're going to see on your exam. If you have any questions, you can send them to me in the comments. And in the meantime, happy studying and have a great day.